In today's explainer, we're opening up the toolbox. We're going to slow things right down and demystify the core mathematical operations that actually power a transformer model. My promise to you is this. By the time we're done, every intimidating, incredibly complex diagram you've ever seen about this architecture is going to become instantly readable. So let's just jump right in. Here's the honest truth about all of this. There's absolutely no exotic math happening inside a transformer. I mean it. There's no advanced calculus you have to learn, no complex theoretical physics involved. The entire model simply relies on taking words, turning them into rows of numbers, and then multiplying and adding those rows together in very specific, predictable patterns. That is literally it.
Because think about it, a neural network can't do math on a word like cat or river. It only knows how to do arithmetic on numbers. So the very first step any language model has to take is turning each word into an ordered list of numbers. We call this a vector. Just picture a single word, like river, being represented as a single straight row of numbers. Each number in that specific list acts like a coordinate, describing some tiny hidden aspect of that word's meaning.
Now, you might be wondering exactly how many numbers are in that list. Well, in the original transformer paper, every single word vector is exactly 512 numbers long. This specific size, this dimension of meaning, is referred to in the architecture as D model. So whenever you see the term D model pop up, just translate it in your head to how many numbers it takes to describe one word.
So what happens if we take a whole sentence, say a 6-word sentence? We simply take those individual word vectors and stack them right on top of each other. Suddenly, our sentence isn't just a line, it becomes a grid. 6 rows down, 512 columns across. We call this grid a matrix. Honestly, just think of it exactly like an Excel spreadsheet. The rows are the words, and the columns are the dimensions of meaning, the features the model is actually tracking. This matrix right here is the fundamental object that the entire transformer operates on.
From this point on, almost everything a transformer does is matrix multiplication. But don't panic, you don't need to do any of this math by hand. You only need to know one simple concept, the shape rule. Think of it like a giant game of dominoes. If we want to multiply our 6 by 512 sentence matrix by another matrix that's shaped 512 by 6, we just look at the numbers. The two inner numbers, 512 and 512, must match perfectly for them to connect. Because they match, the operation is totally legal. Then the two outer numbers, the 6 and the 6, survive that collision and they become the shape of our brand new resulting matrix. Inner numbers cancel out, outer numbers survive.
But here's the catch, and it's a big one. Normal multiplication, 3 times 4 is the exact same as 4 times 3. But with matrices, order strictly matters. If we swap the order around and multiply the 512 by 6 matrix by the 6 by 512 matrix, let's look at those inner numbers. They're now 6 and 6. They match, so yep, it's illegal. But look at the outer numbers this time. They are 512 and 512. The output has completely changed size, blowing up into a massive 512 by 512 grid. So sequence is absolutely everything here.
Let's look back at our smaller 6 by 6 matrix result for a second. What exactly is sitting inside one of those 36 little cells? Well, every single cell is the result of what's called a dot product. To calculate it, you just take one row from the first matrix and one column from the second. You multiply them position by position, first number times first number, second times second, all the way down the line. Then you simply add all 512 of those results up into one single solitary number. That one number lands right in the cell of the output grid.
Now what's truly fascinating is what that dot product actually represents geometrically. A dot product is really a measurement of directional alignment. Think of two people out for a walk. If they walk in the exact same direction, they're perfectly aligned, and the dot product gives them a massive positive score. If one walks north and the other walks east, they're moving perpendicularly, totally unrelated, so the score is basically 0. And if they walk directly toward each other, they are opposed, resulting in a negative score. The dot product captures exactly how aligned two vectors are.
So tying this all together, when the transformer computes that 6 by 6 grid of dot products between the words of our sentence, it isn't just crunching random math. That grid is literally a table of how related every single word is to every other word in the sentence. A huge positive number means two words are highly aligned in meaning or context. This relatedness table, it's the pure, raw material of attention. Now, if you go and read the original paper, you're going to hit a wall of alphabet soup notation pretty fast. But I promise, it's just shorthand for everything we just discussed. First, you'll see Q, K, and V.
Those stand for query, key, and value. Honestly, don't worry about their deeper conceptual meaning just yet. For right now, all you need to know is that all three of these start out as exact copies of our original 6 by 512 sentence matrix. They are literally just sentence-shaped grids of numbers. You'll also notice a little T hanging out next to the K matrix, written as K transpose. Again, this isn't some deep, mystical math, it's just a shape-fitting trick. Remember our dominoes? If we try to multiply Q, which is 6 by 512, by K, which is also 6 by 512, the inner numbers don't match. It's illegal. So, we use a transpose to simply flip the rows and columns of K. It becomes 512 by 6. Suddenly, the inner numbers match, the matrices can legally connect, and boom, we can generate our 6 by 6 relatedness grid.
Right after we compute that grid, the formula tells us to divide every single number by the square root of the key dimension, which is written as root d sub k. Why do we do this? Well, when you multiply and add up 512 numbers, the resulting dot products can become incredibly, dangerously large. Massive numbers will actually overwhelm the neural network and make it stop learning altogether. So this division is just a simple stabilizer. It shrinks those massive scores right back down into a sane, workable range.
Once we've stabilized everything, we pass those numbers through a neat little function called softmax. Softmax takes a row of raw scores and beautifully squashes them into positive percentages that all add up perfectly to 1. It basically takes our relatedness grid and translates it into clean, highly readable attention percentages. It spits out something like, hey, word 3 is currently spending 60% of its attention on word 5 and 30% on word 2. And this brilliantly illustrates the whole picture. The single most famous equation in modern AI is really just a shorthand recipe of the simple, plain English steps we just built together. Step 1, compute the relatedness grid by multiplying Q by K transpose. Step 2, stabilize those raw scores by dividing them. Step 3, convert them into clean percentages using softmax. Step 4, use those percentages to blend the values by multiplying by V. That right there is the entire mathematical foundation of the transformer's attention mechanism.
But wait, step back for a second and look really closely at what we've actually done here. We stacked words into rows in our matrix, sure, but nothing in our shape rules and nothing in our dot products actually cared about that sequence. If you swap two rows in the input, the dot products would come out exactly the same. So that leaves us with a massive, glaring question. If the math entirely ignores the sequence of the text, how on earth does the model know the difference between the dog bit the man and the man bit the dog? Think on that, because figuring out how the model actually understands sequence is exactly where this brilliant architecture goes next.